Okay, hi everybody. So today we're going to do 5.4, which is the Fundamental Theorem of Calculus, which is as important as it sounds. So the Fundamental Theorem of Calculus is something that you're going to be using from now till probably forever in this calc series. And there's actually two parts to it. One part we already kind of did earlier, which was basically the evaluation theorem. And some textbooks will swap part one and part two, but it doesn't matter because the Fundamental Theorem of Calculus just has these two parts. So it doesn't matter if part one is actually part one or part two, but I'm going to be consistent with the book because they reference this for your homework. And so for part one of the Fundamental Theorem of Calculus says that if you let f be continuous on an interval ab, then the function g is defined by g of x, which is equal to the integral from a to x of f of t dt from a to b for our x values. And so I want you to note something here, and that's that here we have our integral from a to x, not a to b. Normally we have our integral from a to b. But in this case, we have our variable right here in our upper bound. So I just want you to note that this is a variable. Okay, so just note that. And so this g of x, which is equal to this integral from a to b of f of t dt, also notice that here we're integrating with respect to t, is the antiderivative of f. So what they're saying here is that if we get g of x, right, and we evaluate g of x using this integral, then if we take the derivative of g of x or the derivative of this integral, then we'll actually get f of x. So what this is really saying is that in order to evaluate that integral, all you have to really do is plug in x into t, and that's going to give you the derivative. So in other words, we will have that g prime of x is equal to the derivative with respect to x of the integral of a to x of f of t dt. And then if you take the derivative of this, you're going to get f of x, which is just this function here with the variable x in it. Now, that seems a little bit too good to be true. So before we actually jump into this assumption, what I want to do is I want to actually run through a few examples to show you that this is actually true. So what we're going to do is I'm going to show you a few examples where we're going to actually evaluate them, and then we're going to take the derivative afterwards so that you believe me. Okay, it's going to work out each time. But just so that you can maybe see where I'm coming from and maybe build that intuition for this example. And then after that, I'll show you that little shortcut way where you don't have to do it. But it's good to know why this works. Okay, so let's do a few examples here. Okay, so let's do this example. So say we had the integral from 4 to x of the square root of t dt. Now, I am eventually going to show you after we take that antiderivative, how when we take the derivative, we'll basically just get the square root of x. But let's go ahead and actually just evaluate this integral using that evaluation theorem that we had before. So what this is really saying is that you have an integral from 4 to x. So if you're kind of thinking about this, when we integrate something, we're looking for the area under the curve between those two bounds, a to b. In this case, we have a variable x. We actually don't know where x stops. So you can think about x being anything, and it could change. So for example, it could be 4 to 5. It could be 4 to 7. It could be 4 to 10, and just keep going. So that's the idea here, is that we don't know how far it is going, but we just know that it's going from 4 to x, some variable that can vary. Okay, so what we're going to do here is if we evaluate this antiderivative, right, what we should probably do first is we should rewrite this so that we get a nice antiderivative so that we're able to do that power rule we learned. Let's make that more higher. So, oops, it should be t. T of 1/2 dt. Okay, so all I did was I rewrote this function here so that I can get the function here so that I can do that backwards power rule for integration. So here, when we integrate this, right, we're going to get 2. So when we integrate this, we add 1 to the exponent, which is adding 2 over 2, and then we divide by it in the front. So hopefully we've all gotten comfortable with doing the backwards power rule. And so that's going to be 2 over 3 t to the 3/2 power from 4 to x. And now we need to evaluate this using that evaluation theorem, which is f of b minus f of a. So when we evaluate this, we'll get, right, we can go ahead and just factor out that 2 over 3 and say that we're going to get 2 over 3. And then we do f of b minus f of a. Our b value here is our variable x, so it's going to be x to the 3/2 power minus 4 to the 3/2 power. So this, all I did here was use that evaluation theorem here. And so here, then we're going to get 2 over 3. Sorry, it's not writing. And then what we're going to do after that is, so when we evaluate this and distribute that 2 over 3 in, we'll get 2 over 3 square root of x cubed minus 16 over 3. So I went ahead and evaluated, and then I distributed that 2 over 3 in. Okay, so this is what we get when we evaluate the integral from 4 to x of the square of, when we evaluate the integral from 4 to x of root t dt. But the theorem here says that if we take the derivative of that function, we will get f of x. So let's go ahead and take the derivative of our function here and see if that's actually true, if we're going to get f of x. And I want you to notice something here, that right here, this value here is actually f of t. So we're going to be taking the derivative of the function we just found, which is 2 over 3 x to the 3/2 minus 16 over 3. All I did here was I rewrote it in terms of power so that when we take the derivative, it's a little bit easier. So if we take the derivative of this, we are going to get 2 over 3 times 3 over 2, look at that, times x to the 1/2 power minus 0. And so these are going to cancel, and at the end of the day, we are only left with x to the 1/2, which is the same thing as root x, which is really the same thing as f of x. Since recall that f of t before was the square root of t. So what this theorem is really saying is that if you are trying to take the derivative of a function using the fundamental theorem of calculus from a to some variable x, all you have to do is say that the derivative of this function here is going to be f of x. Just plug in the x instead of the t value. Okay, we'll do one more example just so you know it's not a. Okay, so let's do another example just so that we can lock this down. So I can show you that definitely if you're trying to take the derivative of an integral from a to a variable x, then you will just plug in that value x. So that's what I'm going to show you now. I'm just going to reinforce the last example with a different example. And so to do a different example, let's try doing a trig function. Those are always so much fun. And just to get some variety in here. So your homework will say to evaluate the integral of this function. Now your job is going to be to use the fundamental theorem of calculus part 1 to easily do it. But like I said, again, before you do it, it's good to understand why it works and so that you can see why it works. So if we differentiate this, right, the derivative of cosecant squared, the antiderivative of cosecant squared is negative cotangent squared. So this would be negative cotangent squared t from pi over 4 to x, right? And now if we use the evaluation theorem and do f of b minus f of a like we did in the last example, this is going to be negative cotangent squared x minus negative cotangent squared of pi over 4. Now, if we evaluate this, this is the same thing as negative cotangent squared x. Cotangent of pi over 4 is 1, and we have a negative and a negative, so that's going to be plus 1. Okay, so this is our result when we take the derivative of our integral here. And now our job is to take the derivative of this function here and show that we indeed do get cosecant squared x. So now we're going to do d over dx of negative cotangent squared x plus 1. So the derivative of cotangent squared x is negative cosecant squared x, but since we have a negative on the outside there, that's going to cause it to be cosecant squared x. And then the derivative of a constant is just 0, so we'll just leave it as that. And this indeed is just f of x because this value here was our f of t. Now we can say that the integral from pi over 4 to x of cosecant squared t dt is indeed just cosecant squared x, which is f of x. And so from now on, if you wanted to find the derivative of an integral like this, when you have the variable just x alone up here or just one variable of the first degree, you can just plug it into that function and you won't have to do any of this middle work. Okay, so now that we know that the Fundamental Theorem of Calculus Part 1 works, let's do an example where we do it super quick just because we know that the theorem works the way that it does. So like I mentioned before, that if we wanted to take the derivative of a function like this, right, all we really need to do if we have a single variable here is just say that it's f of x instead of f of t. So let me demonstrate that with a very simple example. So here I showed you that if you do in fact evaluate the integral using the evaluation theorem, and then after that you take the derivative, you just get f of x. So now since we established that, we no longer have to kind of do that process again, unless I specifically ask you to show me why it works, right? So let's do another example, and this one will be like super quick. It'll be like a minute. It'll probably take me longer to write than to actually do it, actually. So let's do an example. This function here that we have is our function f of t. So f of t equals e to the t squared minus 1. Okay, so we were able to see before that when we have a function, when we have an integral from a constant a to a variable x, that instead of, we can apply the fundamental theorem of calculus and just find f of x. So since f of t, so this is how you're going to write this, so that I know you know where it's coming from. So since f of t, and I'll just rewrite this so that you see how you should write it, equals e to the t squared minus 1, we could say by the fundamental theorem of calculus, and then we have to say part 1 because I haven't showed you part 2 yet, but we will have a part 2. Then this has to be true. Then g prime of x is equal to f of x which equals e to the x squared minus 1. Oh, sorry. Yes, minus 1. And so all we have to do here, if you've noticed, is all I did is I didn't even really do any math. By that theorem, I can just replace my t's by x's to get that derivative of this function. So anytime they ask you a derivative of a function that has this form, this is what you're going to do. So actually, let's just do one more just to lock it in. Because really these don't take too long. They were 3-liners. So let's do another example. One more, it doesn't hurt. More examples, the better, right? Let's see, let's do. So now you can say by fundamental theorem of calculus, and you could go ahead and keep saying, you know, this whole thing, part 1. Or you can just abbreviate it by P1. Whatever, as long as you tell me how you're getting this value. And then say that g prime of x is going to equal 1 over x cubed plus 1. Easy peasy. All we did was replace those t values by x. Super easy. But now the problem is that fundamental theorem of calculus only works this simply when our variable here is just a simple variable like x. But if we have a different value there, let's say we have x plus 1, or x squared, or x cubed, or the sine of x, it doesn't actually work as simple as it does when we just, you know, plug in that value for x. And the reason for this is because we have some kind of like a chain rule going on here. And so if you have a function, and this is really what's going on in the background. So let me show you. So to apply the fundamental theorem of calculus, and this will work each time, all the time, is that to differentiate g of x, which is equal to a times from a to p of x, some function p of x. Technically, x is a function. It's just a function of just itself, just x. There's nothing exciting going on there, and that's how we're able to do it so easily. Is that you need to apply this. When you apply it, g prime of x is always going to equal f of p of x, so that function of x, times that derivative of your function. So really what's happening, we've actually been doing this the whole time. It's just that the derivative of this function here is just 1. So this part is non-existent, right? So basically that's saying that this will work each time, but I just wanted to show you that simple case so that you understood where it was coming from. So now let's do an example where we can't actually, you know, just plug it in and then call it a life. We can't just do that. So let's do another example. Okay, so now let's do an example where our variable, our top boundary is, I said that weird, our top boundary is not just x. So when we actually have to use that chain rule. And remember, you're using that chain rule in the background all the time. It's kind of like when you did derivatives. You always have to do chain rule, but if you have something simple like sine of x, you take the derivative of the inside function. Well, the inside function is just x. Why would you, you know, you don't really think about it, but you are doing it. The derivative of the x is just 1, so you don't actually see that chain rule happening. So let's go ahead and do this example, which is the integral. So let me actually phrase it correctly. So let's find d dx of 1 over, from 1 to x to the 4th. So notice here that our variable function is x to the 4th now and not just x, of secant t dt. Okay, so I'm actually going to introduce something called a u substitution right now, just because when we go over to 5.5, it might make it a lot easier for you to see. So what I'm going to do here is I'm going to let u equal x to the fourth. And so then the derivative with respect to x of the integral from 1 to x to the fourth of secant t dt is now going to become d over dx from the integral from 1 to now u, since we're replacing that u. Well, actually, let me keep it consistent here with the color of secant t dt. But now I want to caution you on something, is that this actually right here, what I just wrote, is wrong because we changed variables. Our variable is now u. So instead of writing this here, we actually have to write something a little bit, we have to write it in terms of the chain rule. Now, you don't have to do this each time, but I'm showing you why it works, right? So I'm not going to write that. I'm going to say that it actually equals the derivative with respect to u, because now we're differentiating with respect to u. But remember, x is still involved in all this, and so we need to do chain rule. From the integral from 1 to u of secant t dt times du over dx. So really what's happening here is, if you think about it, this is okay, but d dx, if we're applying chain rule, is really the same thing as d. Let me move this over so I have a little bit more room, but is really the same thing as du times du dx. Think about it as like a funny little chain rule. This is still over here, we still have d dx, which is what's going on here. I just wanted to write it in terms of that chain rule because we are going to have to take the derivative of u with respect to x. Okay, and so now let's apply that theorem. So this is going to equal secant u times du dx. And now what's the derivative of u? That's just x to the 4. So here's u. So the derivative of u with respect to x is just 4x cubed. But before I do that, so it's just, so we all agree, let me actually put it on the side here, that du over dx is equal to 4x cubed. So that's the part that we're actually going to go ahead and plug in for this part. And now that we evaluated it, we can replace u by what it was, because remember that we wanted to find d dx of this function here in terms of x, not u. U's just helping us find those values. Okay, so here now this is going to be secant, and now I'm going to bring back the original variable x to the fourth. All I'm doing here is replacing, and then times the derivative of u, which we calculated on the side here, which is 4x cubed. And now, because, you know, we're awesome, we want to write this neatly. This is going to be 4x cubed times secant x to the fourth. And that's our answer. That's our, oops, I don't know if it's because it's hot, but I keep messing up my iPad. My hands are sticky. I don't know. Gross. I should go wipe this down. But yeah, I know it was a little confusing. So I'm going to do another example. Okay, so let's do this example with this integral. And so here we need to apply the Fundamental Theorem of Calculus, part 1, in order to find the derivative of this function here. So we are trying to find the derivative of the integral of x plus 3 of 3t cubed minus 1 dx. Now, I'm going to go ahead and give you the answer to this for now. We need to try to find the derivative of the integral from x to x plus 3 of 3t cubed minus 1 dt. And for this, I gave you the answer just so that we can go back and check our work for this. But here we're going to try to apply the fundamental theorem of calculus, but we have a little bit of a scenario here because for the fundamental theorem of calculus to work, we need to go from a constant, right? From a constant to a variable here. So the x plus 3 isn't really the issue. The issue really is that we have an x value here and an x plus 3 value here too. And we know that if we have a different function other than the function that we have, then for the b value for our upper bound, then we just, do a u substitution and apply chain rule. But for this, it doesn't actually work as nicely, and we have to do a little bit of tricks for this. So what I'm going to do is I'm going to go ahead and use my properties of integrals in order to manipulate this function here so that I'm able to apply the fundamental theorem of calculus part 1. And so what I'm going to do right now is we learned that you can separate the integral. So what I'm going to write here is I'm going to do, this is going to equal the derivative with respect to x. And I want to evaluate from, and now I'm going to do from x to 0 of 3t squared minus 1 dt. And I'm going to add the integral from, I'm going to add the derivative with respect to x, take the derivative with respect to x of the integral from 0 to x plus 3 of that same function, which is 3t squared minus 1 dt. Now, this helps us out just a slight bit. We still have to do a little bit more work in order for us to apply it. So notice here that here we're still starting off with an x value and not that constant. We need to start with a constant here, not that x value. Good news is that we do have a constant up here, and there is an integration property that allows us to flip it. So we'll go ahead and do that for that one. And for this one, it's okay. We can just simply just apply the fundamental theorem of calculus here. But we still need to do that u substitution. Okay, so now what we're going to do is I need to manipulate this piece here in order to be able to apply it just like I will for the second piece. And notice that this statement here is equivalent to this statement here because my bounds, I'm still integrating that same function here, but my bounds are going from from x to 0. So remember, my bounds started at x, and now I'm going to add from 0 to x plus 3. So in reality, I'm still going from x to x plus 3. I'm just writing it in a different method, in a different way, sorry. And so now I want to rewrite this part here so that I can get a constant and then my variable so that I can apply a fundamental theorem of calculus part 1. And so in order to do that, recall that when we talked about some of the properties was that if we had, if we wanted to switch the bounds, we can. It's easy. We can just switch the bounds. Instead of going from x to 0, we're going to go from 0 to x. But if we do decide to do that, then we have to tack on a negative in front of it. Okay, so we're going to do, let me do a negative, and then we still have the derivative with respect to x that we're still evaluating. And it's going to be 3t squared minus 1 dt. And then this is going to be plus dx from 0 to x plus 3, 3t squared minus 1 dt. Okay, now what we need to do is we are going to go ahead and do that u substitution here. Again, you don't really need to. You can still just do this application for FTC and say that the derivative is just going to be f of that function p of x times the derivative of that p of x, which is really just doing a u substitution. And so what I'm going to do here is I'm going to, actually, yes, let's do it that way so that you can, no, we'll go ahead and do the u substitution. I want to get in a good habit just because u substitution is coming up, and I just want to, you know, keep practicing substituting in u's. So I'm going to let u equal x plus 3. And so that means that when we take the derivative of it, of du, so if we do du dx of this function here, we're going to just get 1. Okay, so here what we're going to do is now for this statement here, we can easily just apply fundamental theorem of calculus. Here we have a constant, and here we have a variable. So to find the derivative of this part here, all I have to do is plug in that x value into f of t. So this is still our f of t here. So this is going to be negative because we still had that negative from when we flipped the bounds. And it's going to be 3x squared minus 1. So that the derivative of this is this from the fundamental theorem of calculus. Now for this other step, I just want to go about practicing that u sub, is this is going to be plus, I guess I should have wrote u here. We'll keep this like this. So it's going to be d du times the integral from 0 to u now, since we're subbing x plus 3 in for u, of 3t squared minus 1 dt times that du over dx, times that chain rule. And so remember that you don't really have to do this. I'll show you a little shortcut right now. So this is 3x squared minus 1. And now I can easily apply that fundamental theorem of calculus, right here for this spot right here. So this means that I'm going to do plus 3u squared minus 1, right? Because I have a constant 0 to some variable of the first degree. And so this is going to stay the way that it is, times du over dx. Now here, that means that we're taking the derivative of this, which is just 1. So we're basically doing we're taking the derivative of x plus 3. So this is going to be negative 3x squared minus 1 plus, and now for that u value, I'm going to substitute what we let u equal, and that's going to be 3 times x plus 3 minus 1, and then times this derivative, which is just 1. And now we're basically done. We just, oh, and I forgot a squared value here. We're basically done. All we have to do now is just simplify, because right now the answer is not matching the actual answer. So let's go ahead and do some simplification here. We're going to get negative 3x over here minus 1. I'm just rewriting. And this is going to be plus 3 times. Now I'm going to factor the x plus 3 squared out to get x squared plus 6x plus 9 minus 1. Okay, and now from here, now we could go ahead and distribute this 3. Why do I have 2 parentheses here? Now I could go ahead and distribute this 3 over and get negative 3x squared minus 1 plus, why isn't it writing? Oh, 3x squared plus 18x plus 27 minus 1. Okay, looking good, looking good. And so now if I look closely and I simplify, well, I have a negative 3x squared here and a positive 3x. Those are going to go away. This should have been a positive 1 when I distribute that negative value. Sorry about that, but this should be positive. Here I have a positive 1 and a negative 1 here, so these are going to cancel out, and so my answer is left with, the answer I'm left with is 18x plus 27. Now, it seems like a lot of work, but it's not that bad. The trick here is you want to be able to apply Fundamental Theorem of Calculus part 1 when you're trying to take the derivative of an integral. Now, the only way to do that, to apply Fundamental Theorem of Calculus, is if we have a constant times some variable or some function here. Now here, I was being a little bit extra, right? I was writing all the notation so that you know and you are become familiar with it. But in reality, what I could have done, and I'll write it in like a different color here, is if I apply that rule that I gave you over here, where we do f of p of x times the derivative of p of x, well, this function here, x plus 3, is technically our p of x. So if we apply that theorem, or if we apply that process of how to do that when we have something that's not just x, or it's not just of the first degree, all we have to do is we could have wrote this, and let me get like a pink or something, is we could have done 3 times x plus 3 all squared minus 1, and then times the derivative of this function here, which is just 1, which is exactly what we got over here. So you could have kind of skipped these steps, but I just want you to see where it comes from, and I want you to get familiar with that u substitution, because it's coming in next section, and it's just a good practice to do it. On your homework, though, you're welcome to do this. Just be careful when you do it. Don't forget to do the chain rule there, okay? And so this is basically as hard as it's going to get for these. So practice, 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 and remember that the trick for those are to go from to go from a constant to some variable or some function up on top so that you're able to apply Fundamental Theorem of Calculus. Okay, so I'm going to stop this video now, and I'm actually going to start a new video for the Fundamental Theorem of Calculus Part 2, which will be really familiar for most of you if you guys watched the video on 5.3. It's very similar to the evaluation theorem we've been doing, so that's good. And then we'll talk about the differences between both parts of Part 1 and Part 2, just so that you're not getting confused, okay? So see you in the next one.